Hello and welcome to our lecture 13, part 1. Today we're going to be talking about energy conservation reference frames. But before we get there, let's do a brief recap of what we learned last time. Last time, we considered 3 different cases of frame transformations. Case 1 is that our reference frame was moving relative to the lab frame at a constant velocity. So we have our lab frame or the platform frame, and our train, which has xrel, yrel, zrel coordinates, was moving relative to the lab frame coordinates x, y, and z at the velocity of vt. And in case 1, vt was a constant. In this case, this was an inertial frame. And what we found is that our equations of motion in terms of the coordinates of the train frame or of the moving frame reduce to the same equations of motion as in the lab frame, because equations of motion look exactly the same way in all inertial frames, so that in the absence of external forces, the velocity of our body stays constant. And conversely, x double dot relative is equal to 0. So we also considered case 2, where the velocity of the train was not a constant. And this is a non-inertial frame. In this case, equations of motion look different in different frames. And in non-inertial frames, we now have effective forces, that are due to non-inertial nature of the frame, or non-inertial forces. So in this case, the equations of motion looked like that. So in this case, we had an effective force due to the acceleration of the frame, so that the acceleration of point mass in a frame that accelerates at the acceleration at was minus at. So what it means is that forces of inertia push back. So if our train is decelerating, it means that at is negative, then the force of inertia will push you forward. So that's why there is a negative sign, because the effective acceleration will be forward. We also discussed the correspondence, first revealed by Einstein, between the forces of inertia and gravity. And so what he postulated is that forces of inertia behave exactly the same way as gravity. In fact, they wouldn't be distinguishable one from the other. And the third case we considered was the case of rotation. And in this case, we considered the case of omega equal to constant. In this case, in the rotating frame, we have been able to write the equations of motion, where now all of the notation drops the rel index or subscript, because otherwise it would be too cumbersome to carry it over. That's why I'm saying that all of this in the rotating frame. So this is actually r rel double dot. I dropped the rel. So mr rel double dot is going to be equal to the sum of all the forces, both physical and fictitious forces of inertia. So it will be the sum of all the forces minus 2m omega v and minus m omega cross r. So this is the Coriolis force, and this is the centrifugal force. And so it is the sum of these two fictitious forces of inertia is what we need to add in order to make the equations of motion work for non-inertial frames. We also showed that this weird-looking relation can be rewritten in a form that is more familiar to us, omega times omega dot r minus r times omega squared. So here you can immediately tell that this will be a centrifugal force because it takes the regular form omega squared times r. And this part is correcting for the fact when omega and r are not perpendicular to each other. So it is making it work for that case. So what did we find that these forces were responsible for in interesting applications? So we considered hurricanes and typhoons, and what we concluded is that in the northern hemisphere, Coriolis force pushes you to the right relative to the direction of motion. And in the southern hemisphere, Coriolis force pushes to left. And because of that, hurricanes rotate counterclockwise. And in the southern hemisphere, typhoons rotate clockwise. Why is that? Well, because the motion of the air sucked into the hurricane, because hurricane is under pressured structure, gets deflected to the right, to the right, to the right. And so this is what creates the swirling motion that is counterclockwise. Whereas in the case of typhoons, the same exact inwards motion results in deflection to the left, and hence in the clockwise rotation. That's all for recap of the previous lecture, and I'm going to see you in section 13.2 of our lectures, where I will solve some example midterm problems. That's going to be useful, wouldn't it be? I'm going to see you soon. Thanks for your attention. Thanks for watching, and don't forget to do the quiz. Bye-bye. Hello, and welcome to part 2 of our lecture 13. Now is the time for us to go over some example midterm problems. So let's get started with that. Let's consider example 1. Suppose that we have two springs of equal length to which a mass m is attached. Each of the spring has length L, and the left spring has the spring constant L, and the right one has a spring constant KL, and the right one has spring constant KR. So these crosses are the attachment points. So the springs are attached, so the attachment points can't move, but the mass can move. So the springs make an angle theta 0 with the horizontal plane, and there is no gravity. So all we have is two springs that make each an angle theta 0 with the horizontal direction, and the length is L, and one of them has KL and the other one has KR for the spring constant. And what we want to do is we would like to find find T and V matrix. So how do we approach this problem? Well, as usual, we write down what the kinetic energy is. And for that, we would need to choose what our coordinates are. And for those coordinates, I choose x and y measured relative to the equilibrium position of the mass. So this will be x, that will be y, and our mass m will be the same. So then once we introduce the two coordinates, q1 is equal to x and q2 is equal to y, so a number of degrees of freedom is equal to 2, right? Once you specified x and y, everything is set. This is a 2D problem. Then we can write down the kinetic energy simply as the sum of its x and y components. And from here, we can immediately write down the T matrix as d to t dx dot squared. So that will give us mass. Same thing for y, and we'll have zeros for the off-diagonal terms because there are no cross terms. There is no x dot y dot term. So for the potential energy, things are more difficult because the potential energy of the system is the sum of the potential energy of the left plus the right spring, and the potential energy of the left spring is KL over 2 times the length of the left spring minus the equilibrium length squared. And the same thing for the right spring. And L is in both cases because in both cases the equilibrium length by definition is the same, just L. So what we need to do is we need to figure out, let's do it on the example of the left spring, what is going to be LL, the left spring length. So that is, we can compute that by writing it out in components. So if we introduce x0, which is projection of the spring onto the x-axis, and if we introduce y0, which is projection of the spring onto the y-axis, then the full length of the spring will be x0 plus x squared plus y0 plus y squared, and we'll need to take the square root of that to give us the length of the third side of this triangle, the hypotenuse. So then we will express x0 in terms of L. So it will be L times cosine theta, both squared, plus x. Oh, no squares. What am I doing here? No squares. Running too far ahead. So this will be theta 0 square plus L sine theta plus y square, all 1/2. And then what do? Well, let's expand the squares and let's see what we're going to get over here. We're going to get L squared cosine squared theta 0 plus 2lx cosine theta 0 plus x squared plus L squared sine squared theta 0 plus 2ly sine theta 0 plus y squared. And all of that, so this is the first one, that's the second one, and we take the square root of that. So first things first, we can combine the L squares. So we're going to get L square by summing up this one plus that one. Then we're going to get the terms that are linear in x and y. So we're going to get 2L times x cosine theta 0 plus y sine theta 0. And then we're going to get the second order terms, x squared plus y squared. And then we're going to close the square root. So now we see that these are higher order terms than these. And what we really need is the linear contribution of our displacements to the changes in the length of the spring. So what we're going to do is neglect the higher order corrections. And we're going to stick with the lowest order corrections. In fact, we're going to expand this by taking L out as a factor. So we're going to factor L out. We're going to get 1 plus 2 x cosine theta 0 plus y sine theta 0 divided by L, all of that to the 1/2 power. Oh, and when we factor it out, of course, we're going to get rid of the square, right? So now we've gotten something that has the right dimensions, and we've gotten a small number plus 1, or rather 1 plus a small number, which is also dimensionless. So then we now can approximately expand, and this was also an approximation, we can approximately expand this, and we're going to find that this is equal to L times 1 plus x cosine theta 0 plus y times sine theta 0, all divided by L. And we're dropping all the higher order terms. And finally, we are getting the result that it's equal to L plus x times cosine theta 0 plus y times sine theta 0. And now, therefore, we can conclude as a result here that delta L of the left spring, which is what is entering here, so we can write it out as 1/2 KL delta L squared plus 1/2 KR delta LR squared. So delta L is going to be equal to L minus L, and that is equal to x cosine theta 0 plus y sine theta 0. So that's awesome. That's great. We have been able to find the contribution of the left spring to the potential energy. Once we plug that into there, we've got it. And now let's write out what will be delta LR by analogy, right? So delta LR will be the opposite of this, because if the mass moves to the right spring contracts, and but y will stay with the same sign, because if mass moves up, the right spring expands the same way as the left spring, right? So we don't have to recompute this, and only if my hands cooperated and wrote exactly what I needed to write, so it will be y times sine theta 0. So now that we've gotten the expressions for delta L's for the left and the right spring, we can get them over to here. And we're ready to write down the V matrix. So, but before that, let's of course write out what the V is. VL is equal to 1/2 KL delta L left, and that will be x cosine theta 0 plus y sine theta 0 squared. VR is equal to 1/2 KR minus cosine theta 0 plus y sine theta 0 squared. And as a result, from here, we can immediately get that V as a matrix, which we can compute from the sum of these, is going to be d2v dx squared. So what will that be? We have x here and we have x there. So we have two contributions to v from x. That will be kl plus kr. And all of that multiplied by cosine squared theta 0. Then by symmetry we're going to get here kl plus kr times sine squared theta 0. And for the off-diagonal terms, we're going to have 2xy cosine sine, right, with the plus. And for the right, it will be with a minus sign, right? So when we do that, we're going to have kl minus kr times sine theta 0 cosine theta 0. And we're going to get exactly the same term over on this side. Okay, that's example number 1. Please check out the quiz. And we're going to move to example number 2 of a midterm problem in the next part of lecture 13. Thanks a lot for stopping by, and I'm going to see you soon. Hello and welcome to part 3 of our amazing lecture 13. Let us consider example 2 of the midterm type problem. So in example 2, let's consider a Keplerian orbit of a planet with a given semi-major axis and eccentricity. So it's going to be an eccentric orbit around star of mass m. So the orbit is given by r equal to a times 1 minus epsilon squared divided by 1 plus e times cosine theta minus omega. So that's our radius. Our energy is given by minus gm over 2a. L is given by gm a 1 minus e squared. And mass of the planet is equal to 1 for simplicity. So first question. What's the speed at pericenter? So pericenter is this closest point of approach, RP. And RP is given here when cosine is maximum 1. So then it is going to be equal to a times 1 minus epsilon. So if RP is that, we can make use of the angular momentum conservation. R times v theta is equal to L equal to gma 1 minus epsilon squared, all square root. If we plug in RP right over here, we can express what v theta is. Right from here, it will be L divided by RP. And L is this and RP is that. So we're going to get gma 1 minus e squared all under the square root divided by a times 1 minus e. So what does this result in? So a's will partially cancel out. 1 minus e, 1 plus e, 1 minus e will partially cancel out. So we're going to get gm over a. And here we're going to get 1 plus e. And here we're going to get 1 minus e. So that is our v theta. So we've found the speed at the pericenter. Now, what else can we do? We can give this particle a kick at the pericenter. So it had some velocity, in the tangential direction, the theta direction, and we're going to give it a kick, delta v theta. Give kick in the amount of delta v theta at pericenter. So, question. What is new? What is the change in the semi-major axis and in the eccentricity? So how do we get to look at that? Remember, we had stellar mass loss, and then we tried to figure out what the properties of the new orbit were. We used the changes in energy and changes in angular momentum to figure out what will be the changes in the coordinates, right? So let's try and do exactly the same thing once again. So first of all, we can write down what is the change in energy. So the change in energy is going to be just that. So we just difference that. Change in VR squared over 2 plus v theta squared over 2 minus gm over r. And you see VR doesn't change because it was 0 stayed 0, r doesn't change because it stayed the same at the pericenter. So the only thing that changes is v theta. So we're going to get that this is equal to v theta delta v theta. So what do we get out of here? We can get delta A out of here. So you can see that delta A is going to be equal to 2a squared v theta delta v theta, all divided by gm. So that's convenient. And then all we need to do to get this, we need to plug in what v theta is at the pericenter radius right into there. Great. Let's now use the angular momentum conservation, and that is r times delta v theta, and that is equal to delta of square root of gma times the square root of 1 minus e squared, and that is at the same time is going to be equal to, let's take all of these derivatives. So if we take the derivative of this guy, we're going to get gm over a, and there will be also 1/2 times 1 minus epsilon squared. And then there will be, we will keep gm over a the same, gma the same, and we're going to take the derivative of this. So that will give us 1 minus e squared, and then we will do the derivative of 1 minus e squared. What is that? That will be minus 2e delta e, right? So we're going to do e delta e over here, and we're going to do the minus sign over here. Minus sign over here. Great. So that is our delta L. Great. So we know what delta v theta is. We know what radius is. Here I need to include, of course, delta A. Great, because I forgot to include that. So let's do this. Square root of 1 minus e squared times delta A. Awesome. Okay, so now I think that there are no more typos and we can move on. What we need to back out of here is, we already know what delta A is, so we're backing out what delta eccentricity is. But for that we would need to plug in delta A here, plug in v theta over here, and that way we'll be able to make everything work. So let's do that. So first of all, radius gets plugged in from there into here. So that will be a times 1 minus e times delta v theta. So here, let us write out 1/2 gm over a multiplied by 1 minus e squared And then we're going to plug this in. GMA E delta E divided by square root of 1 minus E squared. So first of all, this 2 gets cancelled with that 2. These two A's get cancelled that A. Here we have, this is really 1 minus E times 1 plus E. So we're going to get a bunch of them cancel out. So I'm going to cancel these 3 out. But as a result, I'm going to write in times 1 plus E, because there was square root of 1 plus E from here, square root of 1 plus E from here. We're also going to cancel out these 2 square roots of GM with that one. So what are we going to be ending up with? We're going to end up with a 1 minus E times delta V theta is equal to A times 1 plus E times delta V theta. And here we're going to end up with minus GMA times E delta E divided by square root of 1 minus E squared. There is A times delta V theta in both cases, so these 1's are going to go away. And then we can cancel through all of the factors of E like that. So then we're going to end up with, well, I guess this is confusing because we canceled the E's. Well, let me do it like that. So if we cancel the E's, we are going to get 2A delta V theta. So we're going to, so there is a minus, so minus A delta V theta remaining from here. There is plus A delta V theta from here, so there are 2 of them. I'm going to move this over to the left, and we're going to get GMA divided by 1 minus E squared delta E over here. And so therefore our delta E, delta eccentricity, is going to be equal to 2A times square root of 1 minus E divided by GMA. Or we can cancel out the A, it becomes square root of GM, and then A will be under the square root. And I need not forget that there is also delta V theta in here. All right. Yep, so that's exactly what we're going to get. So there is a delta V theta here and delta V theta over here. Yeah, so this is our answer, that delta E is equal to that. So you see it's related to what we know, to the eccentricity, to the semi-major axis, to the parameters of the orbit, times the change in delta V theta. So that's exactly what we were asked to find. So this is a second example of what we could be solving on the midterm. And now I'm going to move on to the next part of this lecture, where we're going to consider frame transformations and energy. So stay tuned, don't forget to do the quiz, and we're going to get there in no time. See you soon. Hello, and welcome to lecture 13.4. So it's part 4 of lecture 13. And we are going to be talking about an exciting topic. How does energy depend on the frame of reference? So let's try and figure that out. So very important problem. So let's consider what seems like a paradox. Let us take a hill and let us take a mass and let it slide up the hill. So in the hill frame, the mass will go up onto the top of the hill, and it will convert kinetic energy into potential energy as climbs hill. Okay, that makes sense. Energy is conserved. Well, let us now jump into a rocket that flies at the same speed as our mass. So suddenly, instead of the mass sliding up the hill, what we will have is that the velocity of the mass will vanish in the frame of the rocket. So because we are co-moving with the mass, its velocity is 0, but now the hill is flying to us with the same magnitude of velocity but opposite in direction. So that is a rocket. Now let's try and see what happens in this case. The hill flies through, gives a kick to the ball, and at the same time the ball climbs the hill. So what we have is ball climbs hill, and both kinetic energy and potential energy both increase. How can this be possible? Did we make energy out of nowhere? Did we get energy for free? So this is in the rocket frame. So what's the solution to this seeming paradox? Well, of course the answer is that in the rocket frame, the hill is time dependent. Therefore, the potential in the rocket frame is time dependent. So it's not an independent of time potential. Therefore, the energy is not supposed to be conserved. So that is okay. Now, let us try and figure out what would be a conserved quantity in the rocket frame. So let's try and write down the Lagrangian. L is equal to 1/2 x dot squared. We, as usual, set mass to 1. So it's kinetic energy minus the potential energy. And potential energy here will be expressed in terms of the height of the hill. So this is going to be y, or the shape of the hill will be h as a function of x, and it will be given by this. So it will be x minus vt. So that if we're sitting at a particular x, then eventually the hill will fly through us from left to right. So that's why x minus vt equal to 0. So a particular part of our potential is going to be flying to the right. X will be increasing as vt. So that makes sense. So what is the relative coordinate to the hill? Well, that's precisely what this is. So xr is equal to x minus vt. That's why it enters here like this. So let's now compute what is the corresponding velocity, how the velocities relate to each other. So in this case, we will write that x dot is going to be equal to xr dot plus v. And then we will be able to write the Lagrangian as 1/2 xr dot, so xr dot plus v squared minus gh of xr. So we have achieved our goal. We have converted the Lagrangian from the lab frame coordinates, from the hill coordinates, to the rocket coordinates. So let us now expand this, and we're going to get 1/2 x dot r squared plus xr dot times v plus v squared over 2 minus g h of xr. So here we can see that v is a constant, so we can throw this away. And we can now compute the conserved quantity, which, as you remember, is the Hamiltonian, which is given by the momentum times x dot minus L, which will be, what's the momentum? It's dl dxr dot. dl dxr dot will be xr dot plus v times xr dot, and we're going to subtract off L, which will be 1/2 xr dot squared minus xr dot v plus gh of xr. And you can immediately see that we will have some terms cancel. For instance, this one cancels that one, and we're going to get that the answer here is going to be 1/2 xr dot squared plus gh of xr. So what we've really gotten here is, this is the energy in the frame of the hill. So this is the right conserved quantity. So you can see we were working in the wrong frame where the energy wasn't supposed to be conserved, and yet by computing the Hamiltonian, we were able to find the quantity that is conserved, which happens to be the energy in the lab frame. So in some sense, no surprise. Things are working out exactly the way they should be working out. So let's try and figure out what happens when a mass collides with a hill. So suppose that we have our x-coordinate, and there is a hill that's flying to the right at velocity v, and we have a particle that is moving towards the hill and is in a collision course with it. So can we figure out what will happen as a result of the collision of this particle with the hill? Will the particle, if it bounces off the hill, gain energy, lose energy? What is going to happen? So for that, we can make use of the energy conservation. So we can denote E as the energy, the Hamiltonian. And so we can say that E is equal to 1/2 of the relative velocity. So what is the relative velocity of the particle with respect to the hill? Well, it is going to be 1/2 x dot is the absolute velocity minus v, that will be the relative velocity of the particle with respect to the hill, squared, plus there will be gh of x minus vt, so that is the relative coordinate. So then let us write down that the energy after the collision is equal to energy before the collision. Energy after the collision will be such that the potential energy vanishes because the hill disappears. So all we care about is making sure that these terms that contain x dot minus v square are equal to each other. So that means that if we have final x dot minus v squared, it should be equal to the initial x dot minus v also squared. And let's see in which case our collision is going to happen. It's going to happen if v is catching up with our hill. xi dot minus v should be negative, right? So we need to put a negative sign over here when we take the square root. But here, because the hill caught up with it, the final velocity of the particle should exceed the velocity of the hill. So xf minus v should be positive. So this is positive, this is negative, but with the minus sign, both of them will be positive. So it means that xf dot is going to be equal to minus xi dot, right, plus 2v. So it means that during collision, particle gains 2v in velocity. We can call this a ping-pong effect. So you can think of it as the hill representing the ping-pong racket, which smashes into the ball that may be flying towards it or maybe not, or it catches up with the ball and gives it extra energy. So if the racket is infinitely heavy, just like this hill, there is no feedback at all on the velocity of the hill. It's just given potential, just like the racket is going to constant velocity. The ball will gain 2v, where v is the velocity with which the racket is moving towards the ball. And this is also known as first-order Fermi acceleration. For instance, we think that this is how particles can get accelerated if they get a kick by the shock. In fact, what we think is happening is in the shock, fluid is converging towards the shock, and the particle gets stuck in the shock and receives this ping-pong kicks from both sides. And if it's stuck in the shock for a while, then in the end it can gain quite a bit of energy through this Fermi first-order acceleration or the ping-pong effect. Thank you for your attention. Do the quiz, and then we're going to be able to move to lecture 14, where we're going to talk about the rigid body, a really interesting new topic. Thank you. Bye-bye.